In Chapter 4, we're going to discuss the average and standard deviation. So first, lots of times we want to summarize our data. So we talked about how to graph our data. Now we'll summarize it with numbers. So there are two main aspects of a list of numbers we may want to summarize, including the middle or center of the data. So why would you want to look at the middle? Well, if you're comparing these two data lists, 3, 5, 6, 7, 7, 8, that's quite a bit different from 18, 19, 20, 20, 22, and 23. The only difference here is the center, or kind of the middle of the data. And we can measure the middle of the data with the average or median. But we also have what's called the spread or variability in the data that we want to measure. Because if you look up at our previous two sets of numbers, notice that they vary about by the same amount. So from 3 to 8, that's a difference of 5. 18, 23, that's a difference of 5. Okay, they're spread out about the same. But these two sets of numbers, 3, 3.1, 3.2, 3.2, and 3.3, that's a very different set of numbers than 3, 5, 7, 7, and 15. Notice my second set is much more spread out. There's much more of a difference between my numbers. So to measure the amount of spread or variability, we're going to talk about standard deviation or range. First, let's go over the average. So the average is one of the most common numbers we'll talk about in statistics. The average is a measure of the center or the middle of the data. To find the average, we're going to find the sum of all the data values. Sum just means add up all the data values. So we add up all the values and then divide by the number of our values. The average is the most commonly used summary statistic for analyzing our experimental and observational data, and the average is also sometimes called the mean. So example 1, find the average lifespan of the first 5 U.S. presidents. Their lifespans are 67, 90, 83, 85, and 73. So what I have to do is add up all the values. So 67 plus 90 plus 83 plus 85 plus 73, and divide by how many there are. There are 5 of them. So if I add those up, that ends up being 398 divided by 5, which is 79.6. So the average lifespan is 79.6 years. If you're a visual person, it might help to think of the average as the balance point. The average will always be the balance point of the histogram. So the histograms for the weights of about 2,700 women in our sample, the average is marked by a vertical line. So here's our vertical line. So that's the average. That's kind of our tipping point. And it does tell us that 41% of the women were above average. So 41% above average. This line is our average. And if 41% are above average, you always have to add up to 100%. So if 41% are above average, that means that 59% are below average. Now let's talk about the median. For the median, half the data values in a list are less than the median and half the data values are greater than the median. Or if you think about it, half of the area in the histogram is going to be to the left of the median and half will be to the right. So to find the median, we're going to go through. First we'll write all the numbers from smallest to largest. And then if the number of values is odd, the median is the middle number. If the number of values is even, the median is the average of the two middle numbers. So, for example, find the median lifespan of the first 5 presidents. Their lifespans are 67, 90, 83, 85, and 73. Remember, we said the first step is we're going to write them in order. So 67, 73, 83, 85, and 90. So what I do is I start working on each end and I cross off the lowest number, then the highest number, and the second lowest, and highest, second highest, and I get to 83 is the middle number. So my median is 83. Example 22, find the median lifespan of the first 4 presidents. That's supposed to say 4 presidents. For the first 4, their lifespans are 67, and if I'm putting them in order, 83, 85, and 90. Okay, now if I start at the bottom, I take off the smallest and largest, and then I go second, smallest, second largest, but there's no number in between. I'm trying to find this number in between, but there's not a number in between. So what I'm going to do is I'm going to take the average of the two middle numbers. So 83 plus 85 and divide by 2, because there's two middle numbers, gives me 84. So the median of that data set would be 84. Now let's discuss using the median versus the average. So for example, here we have the scores for first exam and intro stats course for 10 students. Here's our data. Let's find the mean and median first exam scores. So I might find the average first. So for average, remember that's just, mean is another word for average. So for the average, we're just going to add up all of our scores. So 80 plus 73 plus 92 plus 85 plus 75 plus all the way up to the last one, which is 90. And then I divide by how many we have. We have 11 of them. Sorry, we have 10 of them. And that gives me 82.1. So that's my mean, or the average. Now let's find the median, but remember, to find the median we have to write all of our scores in order. So the smallest is 55, then 73, 75, 80, 80, 85, 90, 92, 93, and 98. Now I'm looking for the middle score. Notice though we have 10 scores, that's an even number, so I'm not going to be able to find the exact middle. So for example, if I was to count 5, 1, 2, 3, 4, 5, and if I count 5 in this direction, 1, 2, 3, 4, 5, my median should be somewhere here. So 5 are below, 5 are above. Because it's in the middle of the two numbers, I have to find the average of those two numbers. So I add them up and divide by 2, which gives me 82.5. So that's the median. So my median is 82.5, my median is 82.1. Now though, we have one student who didn't take the exam. His score is 0. With his score added to the data set, what is the mean and median? So let's find our mean. That's the average first. So I'm going to add 0 plus 55 plus 73 plus, I get up to the top, plus 93 plus 98, and divide by how many we have. Now we have 11 people. I put that into my calculator and I get 74.6. Notice my average went from 82 all the way down to 74. Now let's find the median. So if I count 5 from each direction, 5 and then 1, 2, 3, 4, 5. Oh look, now we had an odd number, 11 people, and 80 is actually in the middle. There's 5 below it, 5 above it, 80 is right in the middle, and so my median is 80. Now this student's score of 0 was called an outlier because it didn't fit with the rest of the data values. 0 was a lot lower than the rest of the exam scores. So now I'm going to ask you which value is affected more by adding 0 to the data set, the mean or the median? Well, my mean went from 82 to 74. My median only went from 82 to 80. So the mean, or average, was affected much more than my median. So we have some vocabulary for that, which is sensitive measures. So the average is sensitive. Outliers are data values, and a long tail can pull the average towards the tail, so the average is sensitive. But the median is not sensitive. It's not as affected by the long tails or outliers. And again, an outlier is an observation that doesn't fit with the rest of the data. Let's talk a little bit more about the average being sensitive. So I have a graphical summary for you where the average is sensitive. So if you have a long right tail, then your average kind of gets pulled up towards the tail, And so your average is going to be bigger than your median, because you're going to have something like the median that has half on each side. But your average gets pulled up towards the tail because of those extreme values, and so your average will get pulled up. So your average is bigger than the median. If you have a symmetric distribution, then the average and median will be about the same. But if you have a long left-hand tail, you're going to have your median that has half of the area on each side, but your average is going to get pulled down towards these small values because they're so extreme that they pull the average. So if your average gets pulled down, it's going to be smaller than your median. And as another example, I have 3 different lists, and for each list, I've drawn the little histogram. Notice that all that's changing is the last number. So we have 1, 2, 2, 3, 1, 2, 2, 5. So my average is 2, 2.53. So the average is changing, but the median, notice the median is 2, 2, 2. So the median doesn't actually change at all. So again, the mean or the average changes more than the median. And because the average gets pulled up by the tails, or it changes more than the median, sometimes if we have histograms that aren't symmetric, statisticians prefer to use the median to measure the center of the data instead of the average. But by far, the average is the most common way. Now it turns out, again, that we want to measure more than just the center. So for example, 25, we have a sample of service times for 2 different service centers. I have the histograms for you and the actual data. Now if you look at this, both service centers have a mean, or average, and median of 4 days for the repair time. But are the 2 data sets the same? No. Notice that the data is clustered much more tightly for this American Service Center. For the National Service Center, it's spread out much more. You can also see that when you look at the actual numbers. Okay, so obviously they don't look the same. The National Service Center is much more spread out. So even though they have the same center, they have a different spread. So now we're going to talk about how to quantify spread. So to measure spread, there are different ways we can measure spread. There's percentiles, there's interquartile range, there's range, which is just the biggest number minus the smallest number. And then there's the standard deviation, and that's what we're going to use a lot in this class. So our standard deviation, which we're going to abbreviate with SD, measures the spread of our data or the amount of variability in the data values. So for example 26, I have my list of numbers 48, 49, 50, 50, 51, and 52. And notice I have this little dot plot for you. It has a much smaller standard deviation than the list 37, 41, 48, 50, 59, 65. Notice I put them on the 2 dot plots on the same scale, and you can see that the second one is much more spread out. And so if it's spread out more, you have a bigger standard deviation. In example 27, I have 2 smooth histograms for you, and they have the same average and median but different SDs. So looking at it, which one has a bigger standard deviation? Okay, it would be this bottom one right here because it's much more spread out. So it has a bigger SD. And to actually find your standard deviation measures spread by looking at how far your observations are from the average. So we have some specific steps to actually compute our standard deviation. The standard deviation is a term that our textbook likes to use. Root, mean, square of the deviations of the data values from the average. First of all, though, what are deviations? Deviations just means the change from the average. And so to find the deviations, it's going to be the differences between each value and the average. So to find the standard deviation, step 1, we're going to find the average. Step 2, we're going to subtract the average from each value to find the deviations from the average. Then we're going to square all the deviations. Then we're going to find the average, or the mean, of the squared deviations. And then we're going to take the square root of the average squared deviations. So rather than give you a really complicated looking formula, they try to come up with the same, which was root, mean, square. But technically you have to do the root, mean, square. Notice that's backwards from our steps. So you do root, mean, square of the deviations backwards. Now I'm only going to ask you to find this by hand once here in class, or once in this video, and we're going to do it once in class, and maybe once on the homework, and that's going to be it. Because we don't like to do it by hand, it's kind of a waste because computers can just do it so quickly. So for example 28, let's find the standard deviation of this data set. So 45, 30, 80, 40, and 55. Number 1, find the average. So my average is 45 plus 30 plus 80 plus 40 plus 55. And you divide by how many numbers there are, and there are 5 numbers. So that would be 250 divided by 5, which is 50. So $50, that's our average. Step 2, find the deviations and square them. We're kind of combining 2 of our steps. So for each data value, I'll write each data value into my table. 45, 30, 80, 40, and 55. Then I'm going to find each deviation from the average. So I take each value minus the average. So 45 minus 50 is negative 5. And then my next value minus the average, so that would be negative 20. My next value, 80 minus 50, that gives me 30. 40 minus 50, that gives me negative 10, and 55 minus 50 is 5. Now we're going to square each deviation. So I just take each of those differences and square them. So negative 5 squared is 25. Negative 20 squared is 400. 30 squared is 900. Negative 10 squared is 100. And 5 squared is 25. Number 3, find the average or the mean of the squared deviation. So how do you find the average or the mean? You add them all up and divide by how many there are. So it's going to be 25 plus 400 plus 900 plus 100 plus 25, and divide by how many there are, which is 5. So this is going to give me 290. Next, take the square root of the average squared deviations. So the square root of 290 gives me 17.026. So that's my final answer. My standard deviation is 17.026. And technically it's in dollars. So a few thoughts about this. Okay, is why did we square the deviations? Well, if you come back up and look at the deviations, and I add these up, so negative 5 plus negative 20, that's negative 25, plus 30 is 5, minus 10 is negative 5, plus 5 is 0. So if I add up all the deviations, I get to 0. And it turns out that that happens every single time. When you add up all the deviations, the positives and negatives cancel each other out. And that's boring if you just get 0 every time. So we square the deviations so that you only get positive numbers, so that when you add the deviations, the positives and negatives. Don't cancel each other out. So that's why you square the deviations. The next question is, well, why did we take the square root when we were done? So first we have to square everything, and then we take the square root. Well, that's why. Because we squared everything. So now we kind of undo it. The main reason why is because we squared our deviations, then our units would be squared. So we take the square root to get back to our correct units. So for example, if your data is about money, you don't want to have your units be dollar squared. That doesn't make any sense. So if we take the square root, then we get back to just dollars. And just as a side remark, some calculators will give you a slightly larger value for the standard deviation. We call that SD plus. And we talk about it in later chapters. There is a reason they do that, but it's not something that you have to worry about. For now, the biggest thing I want you to remember is that the standard deviation measures how far each value is from the average. Now let's get a little more technical. Okay, so for example 31, let's consider our following data set 1, 3, 5, and 7. If I add 7 to each data value, what happens to the data, the average, and the standard deviation? So what actually happens here? So if I add 7 to each data value, then 1 plus 7 would be 8, 3 plus 7 would be 10, 4 plus 7 is 11, 5 plus 7 is 12, 7 plus 7 is 14. So I literally added 7 to each data value. So now what's going to happen to the average? So if I find the average, I would have to do 8 plus 10 plus 11 plus 12 plus 14 and divide by how many there are, which is 5, and it turns out that that is 11. That's kind of interesting, right? Because 4 plus 7 equals 11. Interesting. I wonder if that always happens. The standard deviation, let's just say I put that into my calculator. We're not going to do that by hand because it just takes too long, but the standard deviation ends up being 2. That's interesting. The standard deviation didn't change. But that kind of makes sense, right? I just added 7 to each number. I didn't really change how far my data spread out. I still go from 1 to 7, that's a range of 6, and from 8 to 14, that's a range of 6. So I didn't actually change how far my data is spread out. My next one, if I multiply each data value by 5, what happens to the data, the average, and the SD? So take each value multiplied by 5. So 1 times 5 is 5, 3 times 5 is 15, 4 times 5 is 20, 25, and 35. So let's find the average. We can do that one by hand, so we may as well. 5 plus 15 plus 20 plus 25 plus 35, and divide by how many we have, which is 5. And this happens to give us 20. That's interesting because 4 times 5 equals 20. Now for my standard deviation, if I put that into my calculator, 2 times 5, it happens to give me 10. 2 times 5 also equals 10. Now this does make sense because my standard deviation, or if you look at the actual data, I went from 1 to 7, that's only a range of 6. But now my numbers are 5, 15, 20, 25, and 35. So that's a difference of 30. So it seems like my data is much more spread out. And in fact, you can see that in these dot plots that I made for you. So this is the original data. Notice it's all tightly clustered together. When we added 7, notice it's like we just picked up our data and moved it. So we just kind of picked up our data and moved it over a little bit. But we didn't change the shape at all. We didn't change how far it spread apart. But when we took our data and we times it by 5, our data is now much more spread out. So the average went up higher and the SD went up higher. So for our next example, let's say, suppose I have a bunch of quiz scores and I decide to give everyone an additional 5 points. What happens to the average and SD? So this is my original, and this is plus 5. Notice, again, it looks like you took the whole histogram and you just kind of moved it over a little bit. So it's like you just picked it up and moved it over 5 spaces. And notice when you look at the average that all they did was add 5 to the average. So 10.27 to 15.27. The SD though didn't change, again because it's like all I did was just shift up my data, so I didn't change how much it was spread apart, so the SD doesn't change. For example 33, suppose I have a bunch of baby heights in centimeters and I decide to change all the heights to inches. To do this, you just multiply each data value by 2.54. So what's going to happen to the average and SD? So here's what it looks like in centimeters, here's what it looks like in inches. So it looks like my average went up quite a bit, and now my data is also more spread out. And it turns out for the average to go from 8 to 20.32, it was actually 8 times 2.54. And the SD was simply 1 times 2.54. And so it turns out that there is a rule about that. Specifically, when we talk about these facts, if we add the same number to each data value, it adds that same number to the average and also the median. But the standard deviation doesn't change because, again, we just kind of shifted up our data. We don't change how far it's spread apart. And multiplying each data value by a positive number multiplies the average, the median, and the standard deviation by that number. So we do have these rules for the average and medians, but they're fairly simple. Okay, and just another note, the units for the average, median, and SD are all the same as the units for the original data. So if you're talking about dollars for your data, then the average, median, and SD will all have units, dollars. So let's practice applying that. In this example, we have students took a quiz that was out of 10 points. The average score was 5 points, the median was 6 points, and the standard deviation was 1.2 points. If I decide to give everyone 3 extra points to help their grades, what are the new average, median, and SD? So basically, we're just taking our data plus 3. So the average and median will each go up by 3. So the average will be the old average plus 3, which is 8. The median will be the old average of 6 plus 3, which is 9. The SD, though, doesn't change. So it's still going to be 1.2. Number 2, if I multiply all the original scores by 10, so that the grades are out of 100, that's why I want to do that, what are the new average, median, and SD? So now we're taking our data times 10. So for the average, we just take the old average of 5, times it by 10, so my new average is 50. For the median, we take our old average of 6, times it by 10, so we're at 60. And for the standard deviation, because we times it by 10, everything is much more spread out, so we're going to take the old standard deviation, times it by 10, and we get 12. So just some useful rules. And finally, this is slightly off topic, I feel, but we're going to talk about cross-sectional versus longitudinal studies. So they have this study that's a representative survey of Americans carried out by the Public Health Service, and note it includes a different group of people each time. That includes data on age, education, income, height, weight, blood pressure, etc. In 1976, the average height of the 20-year-old man was about 70 inches. The average height of a 70-year-old man was about 68 inches. So the question is, does growing old cause you to shrink by 2 inches? No. So what is our explanation here? Of course, some people do shrink a little bit because of when they get older, but usually it's only a fraction of an inch. They're not shrinking 2 inches. So the difference in these average heights is due to the fact that there are different groups of people who grew up in different time periods. The youngest members of the study were born in the late 1950s and grew up in the 1960s. The oldest members were born about 1905 and grew up during World War I. And so this is actually evidence that Americans have been getting taller over time, presumably due to better nutrition and health care. So the study was a cross-sectional study because it consists of a cross-section of the U.S. population at some time point. And that just means they looked at lots of different groups at the same time. Cross-sectional studies give us kind of a snapshot of the population at one moment in time. A longitudinal or cohort study is one in which we follow a group of people over time. And if you want to draw conclusions about what happens over time, you must have a longitudinal study.